Okay, let's dive in. Today, we are getting into the weeds of precision engineering, and we're tackling one of those problems that can be just incredibly frustrating and costly in modern manufacturing.
Deep hole drilling.
Exactly. Drilling deep holes, we're talking about parts for aerospace, for medical devices, high performance engines.
Yeah, places where a single failed hole means you might be scrapping a workpiece that's worth tens of thousands of dollars.
Right. And when you look at CNC machining, it almost seems like the physics of drilling a deep hole are, I don't know, actively conspiring against you.
They really are. The core engineering problem is this really vicious combination of two things. First, you have this rapid, intense heat buildup in a very small space.
And second,
You have no way of getting the waste material, the metal chips, out of that hole. They just get stuck.
so for decades, shops around the world, they tried to solve this with what looks like a simple solution. Just blast more coolant at it from the outside.
Just flood the area.
Yeah.
It seems logical.
But the source materials we've looked at make it absolutely clear. That standard method, it fundamentally fails when the geometry gets tough.
It does. And there's a surprisingly specific point of failure. It's almost like a rule. The moment the depth of that hole goes past 3 times the diameter of the drill, you hit a wall, a thermal and mechanical wall.
And the solution isn't just more external cooling, it's a complete rethinking of the strategy.
It has to be. Which brings us to the core technology here. Through-Spindle Coolant, or TSC.
Right, so this is a system that doesn't spray from the outside. It delivers a high-pressure jet of fluid directly through the tool itself.
Right to the cutting edge, exactly where the work is being done.
So TSC is doing, what, 3 jobs at once that external cooling can't?
That's a great way to put it. It's stabilizing the temperature, it's powerfully evacuating those chips, and it's lubricating everything right at the contact point. Without that internal approach, you physically can't do continuous high-speed production on deep holes.
So that's our mission for this deep dive. We need to decode why this internal system is so essential. Why isn't it just an optional extra? And I guess, why does that traditional method, which looks so good on the surface, fail so completely when the hole goes deep?
Well, it's really the illusion of effectiveness.
What do you mean?
Visually, standard flood cooling looks like it's doing an amazing job. You see this cascade of fluid, it's washing over the entire setup. It looks very dramatic.
But it's not actually getting to where it needs to go.
Not at all. As soon as that tool starts moving into the workpiece, that external fluid becomes almost completely irrelevant to the actual cutting tip.
Our sources call this the application point problem. It doesn't matter how powerful your external pump is, the coolant just can't get inside that deep, confined hole.
Exactly. The geometry is actively working against you. First, the body of the drill itself is basically a plug. It's physically blocking the flow.
Okay, that makes sense.
But second, and this is kind of counterintuitive, that drill is spinning incredibly fast.
Right.
And that rotation, it acts like a little fan. An inefficient fan, maybe, but it's powerful enough to literally blow the coolant away from the entrance of the hole.
So it's not just failing to get in, the tool is actively fighting it. It's pushing it away.
It's actively rejecting it. And this brings us to that really crucial data point, that 3 times diameter rule. The moment that drill gets deeper than 3 times its own diameter, the efficiency of that external coolant just plummets.
How much are we talking?
The drop is huge, something like 60 to 66%.
Wow.
So think about that. 2/3 of the fluid you're pumping is doing absolutely nothing for thermal control where it matters most. For all practical purposes, that tooltip is operating bone dry.
Bone dry inside what is basically an oven. That sounds like an immediate recipe for disaster. I mean, the consequence has to be massive thermal stress, right? Expansion.
Oh, absolutely.
Ugh.
The heat instantly expands the cutting tool.
Yeah.
Now that expanded tool starts rubbing against the walls of the hole, which of course generates even more friction.
And even more heat. It's a feedback loop.
It's a self-perpetuating cycle of destruction. And at the same time, the workpiece itself is heating up and deforming.
And the practical result of that on the shop floor is that operators have to fall back on those horribly slow, inefficient pecking cycles.
The pecking cycle is a strategy of desperation. It really is. You drill a tiny bit, maybe a few millimeters.
And you pull the tool all the way out.
All the way out. You hope some chips fall out. You hope things cool down a bit, and then you go back in. Imagine doing that hundreds of times for one hole.
And if we connect that to the bigger picture, that reliance on pecking, it kills your continuity. You're slowing down production to a crawl.
You're introducing risk every single time that tool re-engages, and you're putting incredible stress on the machine's axis. This is why internal cooling, TSC, isn't just about a better hole. It's a requirement for any kind of serious, efficient manufacturing.
But hold on, even if we solve the heat, what about all that metal dust? You mentioned the chips. Our sources say those chips are maybe an even bigger cause of tool failure than the heat is.
They are the silent killer,
Yeah.
absolutely. Because when you're drilling a deep hole, physics is not your friend. Gravity is not going to help a chip climb 10 centimeters up a narrow shaft.
Yeah.
So with conventional drilling, maybe the external spray scatters a few chips right at the surface. But deep inside that hole, they just pile up. They get stuck in the flukes.
And they start grinding against the tool and the walls.
Right. And then those trapped chips get recut by the tool, which is a phenomenon called secondary cutting.
And that's terrible for the tool, right? It increases wear.
Massively.
Yeah.
And it ruins your surface finish. You get scratches, poor quality. It's a mess.
This is where that internal cooling really changes the game then, because it's not just a heat solution.
It's a mechanical solution. It's about force. We stop hoping gravity will help, and we introduce a massive amount of hydraulic force. We're talking about pumping fluid through the spindle at very high pressure,
How high?
typically between 20 and 70 bar. So that's roughly 300 to over 1,000 psi.
Okay, for perspective, a car wash pressure washer is maybe 200 psi on a good day. So this is serious force being channeled down a tiny hole inside the drill itself.
It's immense. And that force is the key. It creates what the engineers call the hydraulic ram effect.
Hydraulic ram.
Yeah, the high-pressure stream shoots out of little nozzles right at the cutting edge. It hits the bottom of the hole, and because it's in a confined space, it has nowhere to go but back out.
So it's forced to reverse direction. It's like a piston of fluid.
Exactly. It becomes this powerful directional conveyor belt of fluid. It just grabs all those chips and blasts them up the tool's flutes and out of the hole. It's an irresistible force.
And the pressure itself probably helps break up the chips too.
It does. It prevents those long, stringy chips that are famous for binding up and snapping tools. A clean hole is a safe hole for the tool.
Okay, that makes a lot of sense. But if I'm a shop owner, I have to ask, this high pressure system sounds expensive. It sounds like another point of failure. What happens if my pump fails or a seal goes and that pressure drops from, say, 70 bar down to 10?
That's a fantastic operational question. And the answer is the system fails immediately.
Conveyor belt just
It
stops.
stops. The chips start packing in, friction spikes, heat spikes, and you're right back in that thermal destruction cycle we talked about. This is exactly why modern CNCs that use TSC have to have integrated pressure and flow monitoring.
It's not enough to just have the pump.
No. The machine has to be smart enough to know if that pressure drops below the critical threshold, and if it does, it has to shut down the operation instantly to save the tool and save that expensive part.
That feedback loop is critical. Okay, let's circle back to the first problem then, the heat. We said the cutting zone is an oven, but the actual mechanism of failure is. It's just fascinating.
You're talking about the vapor barrier.
Yes, this is where it gets really interesting for me. The temperature gets so high so fast that the coolant doesn't even cool anything. It just boils on contact.
Instantly. And it creates this little layer of steam. That's the vapor barrier. And it sits right between the hot tool and the liquid coolant that's trying to get to it.
Like a thermal shield.
It's a perfect insulator. It actually traps the heat against the tool and physically prevents the liquid from ever touching the metal. So even if some external coolant got near the hole, it wouldn't have the force to punch through that layer of high-temperature steam.
So just to recap, we have a physical block from the drill body.
Yep.
A mechanical block from the fan effect of it spinning,
Right.
and now a thermal block from this vapor barrier. It's like triple jeopardy for the drill bit.
That is the perfect way to describe it. But that high-pressure internal coolant, that 20 to 70 bar stream, is designed for one thing: to penetrate that barrier. It has the force to blast through the steam and make direct contact with the metal.
And that direct contact must stabilize the environment almost instantly. How does that translate to the actual life of the tool? Because these drill bits are not cheap.
The impact is profound. You're stopping multiple types of wear all at once. First, you stop the basic thermal wear, the softening of the cutting edge. But you also stop things like diffusion wear.
Which is when?
That's when it's so hot that atoms from the tool material literally migrate into the chip, weakening the tool structure. And you stopped adhesive wear, which is when bits of the workpiece actually weld themselves to the tool edge for a millisecond before breaking off and taking a piece of the cutter with them.
So these are all major factors that shorten tool life. The effect on the bottom line for a machine shop must be huge.
It's staggering. Studies show pretty conclusively that this kind of focused internal cooling can extend the life of a tool by more than 200%,
200%. So you're tripling the life of your tool.
at least, just by making sure the coolant gets to the right place at the right pressure.
That just completely changes the economics of the whole operation. You're not just saving money on tools, but because the edge stays sharp, you can run the machine faster, more aggressively.
Exactly. It's a double win. With the old method, you slow down to save the tool. With TSC, you save the tool while you speed up.
Okay, so we've protected the tool, we've cleared the chips, we're running at high speed, but none of it matters if the final hull isn't perfect. Rough finishes, chatter marks, wrong size.
The quality killers. And yes, internal cooling acts as a huge process stabilizer here too. First, think about lubrication.
Right.
That high-pressure system forces lubricant directly into that tiny gap between the cutting edge and the wall of the hole. That drastically reduces friction.
And less friction means you prevent that built-up edge, the BUE, where material sticks to the cutter.
Exactly. A clean edge means a clean cut, which means a smooth finish.
Yeah.
That's non-negotiable for, say, a fuel injector or a medical implant.
And the pressure itself must have a stabilizing effect.
It does. It adds a damping effect. It's sort of.
Yeah.
It makes the whole cutting action more rigid and suppresses vibration. By eliminating the thermal roller coaster and steadying the cutting forces, you get rid of those ugly chatter marks on the inside of the hole.
That brings up a really important question, especially for the high-end stuff. How does temperature affect the final measured size of the hole? Because when your tolerances are in microns, dimensional accuracy is everything.
This is arguably the most critical benefit for preventing scrap. It all comes down to thermal expansion.
Heat makes things grow.
Simple as that. If your workpiece gets really hot during drilling, it expands. You drill a hole that is the perfect size for that hot expanded part, but then it cools down.
And when it cools, it shrinks.
The whole part shrinks.
Yeah.
And the hole you drilled is now undersized. It might only be by a few microns, but for a mission-critical aerospace part, that's scrap. You have to throw it away.
And TSC prevents this because it's constantly pulling heat out of the part.
Instantly, it keeps the workpiece thermally stable at or near room temperature for the whole process. So the dimension you program into the machine is the dimension you actually get when it's measured. That guaranteed accuracy is why TSC stops being a luxury and just becomes a fundamental necessity.
What a fantastic deep dive. It's really clear that this whole process is a constant fight against physics, against heat, debris, and vibration.
And the message from all the data is just crystal clear. Through-Spindle Coolant isn't a premium add-on. For quality and speed in deep hole drilling, it is the only way. The solution has to come from the inside out.
We've seen it delivers, 4 major improvements all at the same time. Temperature stability that beats the vapor barrier.
Powerful hydraulic chip removal.
And massive extension of tool life, over 200%.
And guaranteed dimensional accuracy by stopping thermal expansion. It turns a slow, destructive pecking process into one continuous high-speed operation.
And that leads us to our final provocative thought for you, the listener. Given that internal cooling is what prevents that thermal expansion and shrinkage, and it's absolutely required for parts where tolerances are measured in microns, consider this.
If the upfront cost of a high-pressure TSE system prevents just one single, expensive, heat-deformed aerospace part from being scrapped, at what point does this necessity officially become the cheapest solution you have?
Something to think about. We'll see you next time on The Deep Dive.